In the last classes, we've been introducing a mathematical language of vector calculus, differential vector calculus, integral vector calculus for describing vector fields and also describing scalar fields. We talked about div, curl, and grad in vector calculus, differential vector calculus. We talked about line surface integrals for integral vector calculus. These quantities help us describe field properties, vector field properties like the flow of the field, like the rotation of the field, scalar field properties like the slope of the scalar field. In today's class, I want to apply um, these methods, provide an example of these methods for a particular field. We've been working in Cartesian coordinates, rectangular coordinates, where we're working with X, Y, and Z coordinates, axes, and unit vectors. We're going to work on a particular field that's expressed in rectangular coordinates, and that field is upstairs here. I'm going to call that field A. The vector field A has an x component and it has a y component. The x component depends on the y coordinate, interestingly. The y component depends on the x coordinate, interestingly. It doesn't have a z component. This is actually a famous field, a famous vector field. This field appears in electrostatics. It appears in magnetostatics. It's the field of a electric quadrupole, what we call an electric quadrupole, or a magnetic quadrupole. You can make an electrical quadrupole with two positive charges and two negative charges. If you arrange the positive charges on opposite corners of a square, the negative charges on the other opposite corners of a square, that creates an electrostatic quadrupole. And in the region of the center of that square, you would get a field that would look like this field, this quadrupole field. You can make this field in magnetostatics. Supposing you've got some bar magnets. If you put the two north poles at the two opposite corners of the square, and you put two south poles at the other opposite corners of a square. So if you walked around the square, you've got north, south, north, south. That creates a magnetic quadrupole, and the magnetic field near the center of that square has exactly this form. So this field, y times the x unit vector plus x times the y unit vector, is an important field, and it's got some important properties, and it comes up in electrostatics and magnetostatics. We're going to work through this field. We're going to work out things like the divergence and the curl of the field. We're going to work out line integrals and surface integrals over closed lines and closed surfaces for the field. And I'm going to remark on some interesting properties of this field. This is a field that we'll discover is actually divergence free. Its divergence is zero everywhere. It's also curl free. Its curl is zero everywhere. And so we're going to discover those properties of the field. Okay. The first thing I wanted to do is to sketch out this field. Now, I actually made two sketches of this field, one on this slide here and one on the next slide. And I used this first slide with the equation for the field to just get a kind of develop a mental picture for what the field looks like. And then I was able to turn it into perhaps a more familiar field, which is field lines on the next slide. So let's take a look at this vector field here. It has x and y components, no z component. And let's imagine walking along a couple of the axes and seeing what the field would look like if we walked along those axes. So maybe to start with, I'll walk along the x-axis. So I'll take a walk that is along this axis here. And I'll ask the question, what does the field look like at this point, a relatively short distance along the x-axis? If I'm on the x-axis, y equals 0. And so if y is 0, and we look at the equation up here, that means that there is no x component to the field. So on the x-axis, y equals 0, no x component to the field, but there will be a y component to the field because x is not 0. And so I've drawn this y component to the field here. If I walk further, well, it'll still be true that I'm on the x-axis, y equals 0. There's no x component to the field, but the y component of the field, which is in proportion to x, will now be larger. And so this is the end result of that reasoning. Imagine walking on the vertical axis here, the y-axis. So let's walk up this axis here. As I walk up this axis, I'm on the y-axis, so that means that x equals 0. If x equals 0, that means there's no y component to the field. If there's no y component to the field, I'm just seeing the x component to the field, and it's in proportion to the y value. So it's relatively small here where the y value is smaller, and it's relatively large here where the y value is larger. So that's my reasoning for those field lines. How about somewhere out here, over to the top right? Well, on the top right, we've got both a x component and a y component to the field because we've got both non-zero x and y values. And those non-zero x and y values will grow from this point here as we walk out to this point here. Really, the field at this point here is going to be some sort of superposition of this field here due to this y value, this field here due to this x value. And so that's what I've drawn here. If this field, and now we've got non-zero x and y values, we're going to get a field that is in the, it has components in the x and y directions. It's going to point up something like this. And if we walk further away from the origin, then those x and y values are going to grow. It's going to point up more, something like this. And so that's how I reason these components. And I'm not going to walk through the entire diagram here, but I sketched out the field directions when I walked around the negative x and y axes and between the lines of 45 degrees between the other directions relative to the x and y axes. And I got all these components here. What you might notice on this is that, let me start over here on the left. It looks like the field kind of sweeps down something like this over here on the left. If I look at those arrows and I think of the flow of those arrows, if I were to start over here on the bottom right, it looks like the field is sweeping across like this. Again, I'm just looking at the direction of the arrows. And that's what the field is doing. And so if I go to the next slide, here's the field line pattern that I deduced from sketching those field vectors. And you see the field lines that are on the left sweeping down from the top to the bottom. The field lines on the bottom that were sweeping from the right to the left. And then the other components that I didn't discuss, field lines sweep up from the bottom to the top on the right-hand side, and they sweep left to right on the top of the plot here. So this is the field lines that is created by this vector field. At the very center here, the field is 0. X is 0, Y is 0. There is no field at the center. The field grows as you walk away from the center, as you walk along the axes. If you walk along the y-axis, the field grows in the x direction. If you walk along the x-axis, the field grows in the y direction. The field also reverses its direction as you walk across the origin. So it's down as we walk across the origin along the x-axis, and then it becomes up. Or if we walk up along the y-axis, it's towards the left as before we cross the x-axis, and then towards the right after we cross the x-axis. So this is what the field looks like, and you can make this field with a collection of charges. Field lines come out of positive charges. Put a positive charge up here on the top left, and put another positive charge down here on the bottom right, and put negative charges upstairs here on the top right and downstairs here on the bottom left. And that's the field pattern that you get. You could do the same thing with bar magnets, north and south poles in the pairs of opposite corners. So that's the field. That's what this field looks like. This is how we're going to visualize it. Now we've got to move on to our calculations. And I think in my slides, I'm going to calculate surface and line integrals first. Now, when we pick surface and line integrals, we're picking a certain closed loop that we're going to evaluate the circulation around. When we pick a surface integral, we're going to pick a certain surface that we're going to evaluate the flux through. So those refer to specific lines, closed lines, specific surfaces, closed surfaces. When we do the divergence and curl, we're going to be calculating the divergence and the curl of the field as a function of position coordinates, as a function of x and y. So we'll be learning what the divergence and the curl look like everywhere on this plot. So those are the local sources of flux and circulation. Okay, so this slide is one slide on my calculation of the circulation of this field around a particular, a specific loop. And I've sketched the loop upstairs here in the top right-hand side. And if we look at this loop, I positioned it on the coordinate axes. The x-axis is running to the right here. The y-axis is running vertically here, and the z-axis is out of the screen here. This is a right-handed coordinate system. My loop, one corner is at the origin, and we can make the loop by walking one unit out along the x-axis. Then we would walk one unit along the y-axis, and then we would walk one unit back in the negative x direction, and then one unit down the y-axis, and that completes the loop. So 4 steps of 1 unit take us around this loop where we're stepping in the x and y directions. Remember, the field is in the xy plane. There's no field in the z direction. There's no field coming out of the screen or going into the screen. The field's all located in the xy plane, and we're going to figure out the circulation of the field as we walk around that loop that's also in the xy plane. I'm going to call this the side number 1. This side number 2, this side number 3, and this side number 4 in my calculation. My goal here is to calculate the circulation around the entire loop, and this is the general expression for that circulation. Here's the indication. There's a line integral around a closed loop. Here, the ds is my general expression for the little line elements that I'm going to add up to walk around the closed loop. And here's the field that I experience as I walk around the closed loop. And remember, in a circulation, the contribution to the circulation is from the component of the field that is parallel to the steps through the field. And so here's the dot product. we said, it's obvious, given our rectangular coordinates for the field, given our rectangular loop that we're going to walk around, that we're going to break this calculation into 4 steps along the horizontal side, label 1, vertical side 2, horizontal side again, label 3, vertical side, label 4. And so that's all I've done here is broken this single closed loop integral out into 4 line integrals for the 4 sides. All the language is still perfectly general. The steps are still ds. The fields are just expressed as the field vector A. Let's go down to the next step. What I did here, if I can remember, is I just replaced the steps ds, this general language for stepping, with the specific steps for my 4 particular paths. And I also added the limits of those paths. So, for example, for path number 1 here, that's in the x direction. So here's the x unit vector. And each little step is an amount dx in the x direction. So this is the size of the steps. And I'm going to step from the origin to a distance 1 along the x-axis. And so that's the integral with the range of the integral, limits on the integral with respect to x. Then I'm going to move on to integral number 2. That's now in the y direction. I'm walking vertically upwards. I'm going to take little steps, dy in the y direction. It's just the size of those steps. And then again, I'm walking from where I start, which is on the x-axis, so y equals 0, to where I'm going to end up. That's at y equals 1. And then I got the same thing for the path number 3. That's where I'm walking horizontal again, but I'm actually, if you look here, I'm walking not from left to right, I'm walking from right to left. So the thing that really changed here in this expression is that I'm now walking in the opposite direction. And so I'm expressing that here. I'm starting out at a x coordinate of 1 and ending up at an x coordinate of 0. And then there's the final step that gets me back to where I started, closes the loop. This again looks like is a step along in the vertical direction, but instead of walking upwards in the vertical direction from 0 to 1, I'm now walking downwards from 1 to 0 here. So that's just express the steps in rectangular coordinates. The next step in my calculation here, what did I do? In the next step, I just carried out the dot product. So as we were discussing, it's the parallel component of the field that contributes to circulation. So I'm carrying out the dot product with the unit vectors that appear in each of these 4 expressions. So this dot product of the vector field with the x unit vector will pick out the x component of the field. This dot component of the field with the y unit vector picks out the y component of the field. And likewise, this is a walk in the x direction, we get the x component of the field. This is a walk in the y direction, we get a y component of the field. Okay, so now I'm going to fill in this 3rd step what the x and y components of these fields are at the particular x and y values that we're located. So when we're integrating this first path, we're always at y equals 0. We're walking along this horizontal line here. So we can fill in the value of ax at y equals 0. So I'll just remind you that we're at y equals 0 here. if we're at y equals 0, then the value of ax is 0. Then we walk vertically upwards here. Vertically upwards here, we're interested in ay. We're at the location here of x equals 1. So if we're at the location of x equals 1 and we're wondering what is the y component of the field, well, it is just 1. And so I filled in that expression. And likewise, for this third path, we're walking in the x direction, but now the x component is determined by the y value. The y value is 1 here. And so we get this integral. And then we walk down the fourth path. Well, there we're walking in the vertical direction. We want to know the x value there, and the x value is 0 as we return to the origin. And so that's that, and that is that. At that point, I got four integrals. I can just carry out those four integrals. These two are 0 at the left and right. The two in the middle are just integrals of dy or dx from either 0 to 1 or 1 to 0. That just gives us a +1 or a -1, depending on whether we've got the limits in this order or this opposite order here. We end up with this sum for the circulation around the complete closed loop. Notice on the first step, there was no circulation. And on the last step, there was no circulation. On steps 2 and 3, there were circulations, but they cancel one another out. And the total circulation around the entire loop is 0. So let me move on to a second integral vector calculus example. This one was the circulation where we integrated around the loop. The next one is going to be a surface integral where we integrate over a surface, and we're going to be calculating flux. Okay, so let's take a breather. I need a breather. And we'll take a look at this plot upstairs here. It's a little more complicated than the last plot where we just had a loop. Now we've got a closed surface. That's again sitting on the rectangular axes, X, Y, Z axes. I've arranged this cube, which is the surface we're going to evaluate the flux through, with one corner sitting on the origin. And then the cube extends in the X direction 1 unit, extends in the Y direction 1 unit, and in the Z direction 1 unit. And we want to calculate the flux of the field that we've been working with through this particular cube. So we want to figure out what is the flux of this field through that cube. Sorry, that's not what I meant to highlight, but that's good enough. I labeled the different faces of these cubes with some sort of notation. And the way I did it is to call this face here the front face, and then there's a back face that we don't see. I called this face here on the right face, and there's one over here that's kind of hidden, which is the left face. And then here's the up face, and downstairs is the down face. And so I wrote down the general expression for the flux through this surface. This is a surface integral. Here's my general expression dA for a surface element. Here's the field. Here's the surface integral. That's a closed surface integral. And this dot product is because I'm trying to evaluate the field that's perpendicular to the surface, which means that it's actually parallel to the surface element vectors. And so this is the integral. And then here, I'm expanding it just in terms of this idea that, well, my cube is made up of 6 different faces, the front and the back, the upstairs and the downstairs, and the left and the right. So I'm just going to break that closed surface integral into these 6 open surface integrals that I'm going to evaluate in my language of rectangular coordinates. That's the reason for doing that. Okay, let me say something before I actually calculate some integrals. There's 2 of them that I'm just going to sort of recognize and make a statement that they are 0. So this field again is in the XY plane. It has no Z component. So there's no field coming out through this front face, no field coming out or going in through the back face, because there's no Z component. And so 2 of these integrals, the one for the front face here and the one for the back face here, have no field passing through them. There will be no field lines passing through those faces. So I just understand that the integrals, the surface integrals of the field over those faces is going to be 0. And so I'm not going to worry about these. These are both 0. The ones that I have to calculate that will have flux passing through the individual faces are what I call the upstairs and the downstairs and the left and the right. And so that's the calculations down here are for, in the first line, the left-right sides, and in the second line, the upstairs-downstairs sides. Let's do the left side. So that's this integral here, and it's this face sort of hidden away in here. Sorry. The first thing I did was, again, fill in what the surface element is for that particular surface. So firstly, this left surface and the right surface are perpendicular to the x-axis. So the surface element vectors are in the x direction. The convention is that they point out of the closed surface. So the one for the right surface will be in the positive right direction, x direction, and the one for the left surface will be in the negative x direction. So that explains the x here. This is left surface and the right one is perpendicular to the x-axis. And for the left surface, there's a minus sign here because out of the surface is to the left in the negative x direction. This will be positive for the right surface. And then my surface elements are just made by little steps in z and y. Those are the directions perpendicular to the x-axis. Those are the ones in the plane of the surface. So this is me just filling in the area elements. And then in the next step here, I filled in what the important component of the field was. So I'm carrying out the dot product of the field in general with the x unit vector. And I'm carrying it out at the location of this surface, and the location of this surface will be x equals 0. Okay, so we want the x component of this field. And if we look upstairs here, the x component of this field will be is determined by the y value. So carrying out this dot product, a dot x hat, just gives me this y here. I've now got just a math problem. I've got to integrate this integrand y with respect to z, and then with respect to y. It's not a function of z, And so I carry that integral out here. And so I just get this integral where the only integral that's left is with respect to y. And then I just got to integrate with y with respect to y. So I'm going to get a y squared over 2. And then I've got to apply the limits. So you're substituting the limits of from 0 to 1. And that finally gives me the half here. And so there is flux through that left-hand face. It's actually into the cube. That's what the minus sign is saying. And its size in some units is 1/2. I then did exactly the same calculation for the right face. The only thing that changes in the calculation for the right face has to do with this unit vector back here, this dA vector back here. Instead of pointing to the left, it points to the right. So instead of a minus sign here, there's going to be a plus sign. That's because the convention is that these vectors point out of the surface, and out of the surface is towards the left for the left face, towards the right for the right face. So the only difference in the final calculation becomes this 1/2. So these are the fluxes through the left and the right faces. I'm not going to bore us all with walking through the same calculation using the same approach for the remaining two faces. That's the upstairs face and the downstairs face. It's exactly the same procedure as the left face and the right face. The only thing that's changing is the DAs. The DAs are now perpendicular to the surfaces are perpendicular to the y-axis, so the DAs are in the y directions or negative y directions, rather than in the left-right case, the DAs are perpendicular to the are in the direction of the x-axis. And so we had DAs that are in the negative and positive x directions. The end result is fluxes through the upstairs face and the downstairs face that are 1/2 and minus 1/2, just like we got minus 1/2 and 1/2 for the left-right faces. So now we got the fluxes through all 6 faces. We can simply add them all up. That's all I did here. 2 of them were 0, if you remember, because there's no field in the z direction. There were no field components through the front and the back faces. The other faces all had components of flux through them. They weren't 0, but when you add them all up, as much flux goes in as comes out, the next flux is 0. And so that's the calculation of a surface integral in Cartesian coordinates. Let's take a moment. Let's take a breather here, just to re-energize. We've done a line integral and we've done a surface integral. Closed line integral, closed surface integral. We found that for this particular field, this quadrupole field, there was actually in the loop that we chose, no net circulation around the loop. Individual bits of it had circulation, but there's no net circulation around the whole loop. And for the particular surface that we've chosen, there's no net flux through that surface. There are flux through certain sides, but they also canceled out. So that was an interesting and kind of intriguing result. We're going to learn a bit more about that when we look at the divergence and the curl, because the divergence and the curl will tell us what the flux looks like and what the circulation looks like locally. That's what divergence and curl tell us. Everywhere in XY space, XYZ space, what does the what does the source of flux and source of circulation look like at every point in XYZ space? Okay, so this first calculation is the calculation of the curl in Cartesian coordinates of this particular field. Here's the field, and we want to evaluate the curl, the cross product of the del vector operator and the vector field A. And we're going to be doing all this in Cartesian coordinates. So this is the partner to evaluating the line integral. So what did I do? This first line I just wanted to write out the curl formally in rectangular coordinates for our particular field. And so I did that here. I noticed, I just caught this. There's a little typo. There should be a plus in here. This first expression in parentheses here, this is the del vector operator in Cartesian coordinates. And then this second expression here, this is a general expression for a field A in terms of its x, y, and z components in Cartesian coordinates. And so this is one way of writing that curl out. And then we said that we can write it actually in a somewhat simpler fashion or somewhat more compact fashion. If we carry out all these cross products and dot products of the unit vectors here, remembering if we carry those out, like x cross x is 0. So that's handy in simplifying a lot of terms that would be in this equation here in the center. And like x dot y is 0. That also would simplify this in a divergence. Anyway, if you carry out the cross products here, you can rewrite the result as this determinant. That's what the vertical lines mean, of this 3 by 3 matrix that has a simple construction. The top elements are the unit vectors, so this is going to make the result a vector. The second row are the first vector in your cross product. It's components, which are just the partial differentials with respect to x, y, and z. And then the third row is the components of the second vector, which in this case is the x, y, z components of the field A. So I've just written that in. In our particular case, right, our field just has an x and y component. And the x component is just in proportion to the y coordinate, and the y component is just in proportion to the x coordinate. And so I can fill that in to the determinant here. And so in this step, and from step 1 down to step 2, I'm just replacing the general expression for the components of the field with my components of my field. AX is Y and AY is X. So that's very simple. Then the next step for evaluating the circulation of my vector field, I just wrote out the determinant of this particular matrix. So the determinant of this particular matrix will have in general an X component that is the difference between this d by dy acting on this 0 and this d by dz acting on this x. And so you see those two terms here and here. So that's the x component. It will also have a y component. The y component, which is here in my little expression, is going to be the difference between this pair, this is getting a real mess, and this pair over here. So the partial differential with respect to x of 0 and the partial differential with respect to z of y. And so that's what you see as these two coefficients here in my determinant. And similarly, as you know, for calculating a determinant, here there's going to be an x component in general to the circulation, and this x component is determined by this term, the difference of this first term here and this second term here. This is unreadable now, I understand it. And these two terms are here. It turns out, right, that, well, this is 0. Well, literally, this field component was 0. And here, the differential of x with respect to z, that's zero. This is also zero. One of the field components itself is zero, and then the differential of y with respect to z is zero. So both of these are obviously zero, and each of their contributions are zero. What about over here for the z component? Well, the partial differential of x with respect to x is not zero, it's one. Partial differential of y with respect to y is not zero, it's one, but the coefficient that's multiplying the z contribution to the curl is the difference in those, and that cancels out too. So the curl is zero. What we just discovered is that this is a curlless field. There's no source of circulation in this field. Now, if I look at this picture upstairs here, I might say maybe it looks like there's a circulation, or does it not look like there's a circulation? Really, that you see in that picture that there's no net circulation clockwise or counterclockwise. For example, the vectors that are pointing up and down, they look like they are rotating counterclockwise. The vectors that are pointing left, right, they look like they're rotating clockwise. There is no net circulation, no rotation of this field. And that's what we've discovered. This is a curlless field. It's a particular field that has the property of being everywhere curlless. That explains why the line integral of the field was around a closed loop was zero. It's not just accident for that particular closed loop. It was actually it's actually a curlless field everywhere. And so any closed loop would have a line integral of zero in this field. Another breather, and we'll move on to the second case of differential vector calculus, which is calculating the divergence of this field. And this is the slide where I've got my calculation of the divergence of this field. And so here's the field. Here's a little cartoon of what the field looks like. And here's my calculation of the field. And I've taken the same three steps, really. In the first step, just wrote down a general expression for the divergence of a vector field in rectangular coordinates. Then I implanted my field, my specific field, and then I evaluated in this case, the dot products. Rather, in the last case, we were evaluating the determinant, which was evaluating the cross products. So let's just walk through these. Here's the del vector operator. It's x, y, z components of the partial differentials with respect to x, y, and z. Here's a general expression for a field in rectangular coordinate language with its ax, ay, az components. Our particular field doesn't have a z component, so I'm going to drop this piece. And our field has a x component that's simply determined by the y value and a y component that's simply determined by the x value. And so I'm just inserting those here. Now I'm going to carry out the dot products of these unit vectors in the del vector operator and these unit vectors in the field. So let's just carry out those dot products. And we're remembering here that x dot x, that's going to be 1, but an x dot y, that's going to be a 0. And so if I carry out the dot product of the x unit vector in the del vector operator with these two terms, I'm only going to get this first term here because x dot x is 1, so I'll get the y, but x dot y is 0, so that goes away. When I carry out the dot product of the y unit vector with my field, well, y dot x is going to be 0, so I'm not going to get any contribution from this piece. But y dot y, that's going to give me unity. And so I get a contribution from the y component of the del vector operator that is just going to be this x here. So that's carrying out the two dot products of the x and y unit vectors. For the z unit vector, well, look, there's no z component. So it's z dot x, z dot y is 0, and so that's the 0 here. My partial differential are now just these two partial differentials, which if I add them up, is going to give me the divergence of this vector field. The differential of y with respect to x, that's going to be a 0. The differential of x with respect to y is going to be 0. This partial differential with respect to z was already a 0, and so we get a 0 for the divergence of the field. We've discovered that this field is divergenceless everywhere. So throughout the space of x, y, and z, this is a divergenceless field. There's no beginnings and ends of the field lines. We found that there was no flux through our cube, i.e. there was net flux through the cube. We found that there was net flux of 0 through the cube as a consequence of the fact that there's no source of field lines anywhere in this particular vector field. So let's just push the chair back and take a moment to think about what we did. We started thinking about an interesting vector field, a quadrupole field, in the XY plane. We sketched out that field. We saw the field line patterns. It was interesting, intriguing. We calculated the line integral around a closed loop and found that there's no circulation around it. And we calculated the surface integral over a closed surface, and we found that there's no flux through it. Those were the two particular specific lines or surfaces which we observed no flux emerging from, no rotation around. We then did the divergence and the curl. We found an explanation for our line and surface integrals being 0 is that this field is actually a divergenceless field. Its divergence is 0 everywhere, and it's just a curlless field. Its curl is 0 everywhere. Divergenceless and curlless fields are special fields. A divergenceless field can actually be represented as a gradient of a scalar potential. That's a mathematical fact, but it has important physical implications that we will be discussing. The fact that the curl is 0 is important too. Curlless fields, I think I said that the wrong way around, actually. I should have said that a curlless field can be represented by a scalar potential. And that's a mathematical fact, and it's very useful. And a divergenceless field can be represented by a vector potential. And that's a useful fact too, that will have physical implications for us. Let's move on to the slides in which I discuss that before I mess up the discussion anymore. So I was trying to describe the fact that a curlless field can be represented by a scalar potential. And specifically, it can be represented by the gradient of a scalar potential. So we could represent our field A, because it's curlless, by a gradient of a scalar potential. And you can do that because the curl of a gradient is 0, and it's always 0. And on this slide, I'm just demonstrating that mathematical fact. Let me show you that mathematical fact. Again, what is the fact? It's the fact that a curl of a gradient of a scalar field is always zero. And that mathematical fact is written down here. A curl, that's del cross, of a gradient of a scalar field, that's the del U, is always zero. And I'm proving that to you on these two lines here. Well, these two lines are proving it to you. But before we just walk through the two lines, before we walk through the two lines and prove it mathematically, let me just prove it intuitively, because in fact, that's how I think of it, how I remember it. And I think it's a compact and useful idea. Look, we said that the del vector operator is both a operator and a vector. So it's a vector that's pointing in some direction. Well, we got a del vector operator on the left here, and we got a del vector operator on the right here, multiplied by some scalar. So the left-hand term in the cross product and the right-hand term in the cross product are both either the del vector operator or some scalar times the del vector operator. The del vector operator is an operator pointing in some direction in vector space. These two vectors, del and del u, the gradient of u, are pointing in the same direction in space. They're both pointing in the direction of the del vector operator. So they're parallel vectors. And if you take the cross product of parallel vectors, just like x cross y or y cross z, sorry, just like x cross x and y cross y, the cross product of parallel vectors is going to be zero. And so I've just reasoned for you that this must be zero because these two vectors on the left and right, the cross product are parallel, and parallel vectors have a zero cross product. So that's a proof that the curl of a gradient is always zero. It's a mathematical fact. To back up that proof, I proved it here by writing out del in Cartesian coordinates, writing out the gradient of u in Cartesian coordinates. Del in Cartesian coordinates is just the three rectangular unit vectors, each multiplied by a partial differential. The gradient of u in Cartesian coordinates is just the three unit vectors multiplied by partial differentials of u with respect to the three coordinates. It's this guy here. I then carried out the cross products of all these unit vectors, right? The only ones that are not zero are, for example, y cross z is not zero. Two different unit vectors. And y cross z gives you another unit vector in the x direction. So one of these two terms is from y cross z, and the other one is from z cross y. So that's how I got these two components here. Likewise, for the y components, the only way to get a y component from the cross products of these unit vectors here is x cross z or the z cross x. So we get two contributions to the y unit vector here. And similarly for the z unit vector. So when we carry out the cross products, we do get pairs of terms multiplying each unit vector that resulted from the cross products. We literally get this expression here. But if you look at these terms, there's a typo here too. This, a minor one, I'll count it as, should be here. These are second order partial differentials, right? These two terms here in parentheses. The first one differentiates with respect to z and then with respect to y, and the second one differentiates with respect to y and then with respect to z. But the order doesn't matter of the partial differentials. These two things cancel out. So this is actually zero. And the same is true for these two terms, right? Again, there's a little typo in here. Move him to the left of the u. The first term is a partial differential with respect to z, then x. The second one is a partial differential with respect to x, then z. These two terms will cancel out as the order doesn't matter. And the final term also has the same feature, and the two terms cancel out. So this is a mathematical proof that the curl of a gradient is zero. The curl of a gradient is zero. Our field was curlless. Our quadrupole field was curlless. So we could, because a curl of a gradient is zero, we could express that field instead of expressing it as the vector field A, we could express it as an underlying potential, scalar potential U. On the next slide, I just show you what that potential is. On the next slide, I wrote out the computation of that potential. I didn't want to work through the computation of the potential. It's not immediately relevant to us here, but I did want to show you just what that potential looks like. Now we've discovered that that curlless field, A, could be represented as a gradient of a scalar potential, an underlying scalar potential. So let me just go on to the next slide, clear that. This is a derivation of what that underlying scalar potential is for our particular vector field. Remember, our vector field was this guy here. This is A. It had X and Y components. Don't worry about the details. I'm just deriving here that you could represent that vector field as a gradient of a scalar potential. And here's what that scalar potential is. It's just xy. There's a simple underlying scalar potential beneath that particular quadrupole field that is simply xy. Well, that's one version of that potential. This will come up later. I don't want to worry too much right now about all this derivation of this. I just want you to note the property that a curlless field can be represented by the gradient of a scalar potential. And we proved that on the last slide by proving that the curl of a gradient is zero. The second mathematical identity that I want to mention, a kind of related mathematical identity, is this one here. So this one says that the divergence of a curl is always zero. This is a second key mathematical identity. Here's the expression for the divergence of a curl of this would be a vector quantity. Remember, the last one was the curl of a gradient, which involved a scalar quantity u. This is a vector quantity. I've called it A here. I think I meant to call it u here and probably u here. But anyway, why would the divergence of a curl of a vector field, why would that always be zero? Why on earth would that always be zero? Well, I've demonstrated in rectangular coordinates here that it is always zero. And it's the same type of proof as the previous case where we demonstrated the curl of a gradient is always zero. We wrote down the curl and the gradient in Cartesian coordinates. We carried out the product as the unit vector. Some are zeros, some are not zero. We ended up with an expression that involved pairs of second order partial differentials that canceled each other out. All those statements apply to this derivation too. Write out uh, the del vector operator in Cartesian coordinates. Write out the curl of this vector field. I wish I hadn't drawn the U's on it here. In uh, Cartesian coordinates. And here they are in Cartesian coordinates. It's a bit more complicated for a curl. Then carry out the various dot products in this case. Last case, it was cross products between all the unit vectors. Some are non-zero, like x dot x is non-zero. Some are zero, x dot y is zero. This is a bit simpler in this case, these dot products, I think. You get three contributions to the divergence of this curl if you carry out those dot products. The three contributions are coming from the x dots x's, the y dot y's, and the z dot z's, because all the others like x dot y and x dot z are zero. So you get three contributions here. Notice each of these three contributions is not multiplied by a unit vector. This quantity here is a dot product of two vectors. It's going to be a scalar. So these are scalar quantities. These are the scalar contributions from the dot products of pairs of unit vectors. And if you look at these contributions, what you discover is that, for example, let's take this partial differential of second order partial differential of AZ. There's a second partial differential of AZ here. The second order partial differentials of AZ are with respect to x and y in both cases. These two terms, this term and this term, will cancel out. The other pairs cancel out, like the y component of the field appears here and here in the second order partial differentials. It's differentiated with respect to x and z in both cases. The order doesn't matter. This and this cancels out. And the final two cancel out too. This proves that the divergence of a curl is zero mathematically. That's not how I remember it. I remember it by, again, a simple sort of more intuitive understanding of this divergence of a curl in terms of the del being a vector. Del is a vector in vector space pointing in some direction. This del is a vector in vector space pointing in some direction too. I am taking its cross product with the field A. The resulting cross product, so del cross A, that's also a vector, and it actually points perpendicular to del and perpendicular to A. So del cross A is perpendicular to del itself. Well, the dot product picks out the parallelness of two vectors. This del here is perpendicular to del cross A. And so this is intuitively, without worrying about a particular representation, rectangular coordinates, this is zero because it's a dot product of two perpendicular vectors with one another. This turns out to be a very useful feature, again, that we'll meet later on in the course, this mathematical property that the divergence of a curl is zero. It means that you can represent a divergenceless field as the curl of a vector underlying vector potential. And this is very useful in magnetism. So this mathematical property means that if we've got a divergenceless magnetic field, we're going to be able to express it as a curl of a underlying magnetic vector potential. And let me just show you for like I showed you for our quadrupole field, which we said could be electric quadrupole field or a magnetic quadrupole field, what the underlying vector potential is for that field, because it was a divergenceless field. So not only because it's a curless field does it have a underlying scalar potential, because it's divergenceless field, it has an underlying vector potential. So let me just go to the next slide, the final slide. Um, I just want you to look at this slide, and the main points are, I don't want to go through all the mathematical derivation of what this vector potential is that underlies that quadrupole field. So I don't want to go through this derivation. I put it there as a matter of record, some sort of legal record. Um, our field looks like this. Spent the whole class on this little field. Unbelievable. Um, our field, vector field, looks like this. So this is A. And here I'm deriving the underlying scalar, a vector field that can be used to represent that field. The curl of this vector potential is this particular field up here. This vector potential is given by this little expression here. It too is pretty simple. It's just in the z direction. And remember, this field was in the xy plane. The field lines are in the xy plane. The underlying potential must be perpendicular to that, because we're going to get the field by taking the curl of this potential. So that's going to give us something that's perpendicular. And so the potential must be perpendicular to the field. And so that's why it's in the z direction. And it's just given by this little expression here. It depends on the x and y coordinates, and is given by 1/2 times the difference of y squared and x squared. And so this is just showing you a particular example of a vector potential that could be used, if useful, and will be useful, to represent a vector field. Anyway, I'm going to finish there. We've covered divergence and curl of a vector field, surface and line integrals around particular surfaces and particular lines of a vector field. We've covered two mathematical identities, that the divergence of a curl is always zero, and that the curl of a gradient is always zero. These are interesting mathematical identities, but for us in the future, they are the portal or the doorway or the window to representing the electrical field as a scalar potential and representing the magnetic field as a vector potential. That's going to be very useful in the future. So I'm just promising you that these two mathematical identities and this discussion about underlying scalar potentials for vector fields, underlying vector potentials for vector fields is going to be useful. We've discussed that. Thank you.